So, let us continue our discussion about about the Newton's laws of motion. So, we are reviewing the Newton's laws of motion in the second week of this course on Newtonian mechanics with examples. In the previous lecture, we sort of introduced some two basic mechanical model system, the point mass and the rigid body, and we sort of took some example and quickly review some very common forces in daily life that we shall encounter in different problems. Now, this lecture, the goal of this lecture is to review the Newton's laws of motion. Now, I am sure that all of you know the statements of the Newton's laws of motion. So, I will sort of take a kind of unconventional route in the sense that I will start with the third law of motion first, then I will go to the second law of motion, and finally, I will go to the first law of motion. Now, this may not the reason for doing that is that we are trying to develop an analysis strategy to solve problem, and from that point of view it is easiest if we discuss the laws in this way. So, let us see let us get started. So, first, what does Newton's third law of motion says? So, basically says that the interaction forces. So, some of the examples we took in the previous lecture. So, it says that the interaction forces always appear in pairs. So, they always appears in pairs. So, this is the statement first part, and these pairs are equal in magnitude and opposite in direction. So, the point is there is never a lone force without a partner. So, by the way, I must mention that Newton's laws of motions cannot be derived from any in some sense. So, these were originally devised based on doing experiments. So, these are kind of inferences from our everyday life experiments, and the point, and this was not very easy because of the biases introduced by because of the fact that we always feel the gravity and the drag force due to the atmosphere we are living in, the frictional force. So, that makes it difficult to sort of deduce the correct laws. So, sometimes maybe that is one reason why the mechanics problems are kind of you find hard conceptually. So, that is why we are trying to emphasize the concepts in this lecture, and then in the coming lectures we will apply those concepts through examples. So, let us understand this statement using this simple example of the book on a table problem. So, the question is, so I have kept a book on this table. So, maybe something like this. So, imagine this is a table and I have kept a book on the table. The question is, what are the interactions on the book? Now, this simple problem is again somewhat difficult to many students, it is very surprising. The point is that there are two separate interaction pairs. Now, we should think in terms of pairs. So, what are these pairs? So, the first set of interaction is between the book and the table. So, I have this, you can do this experiment yourself, put a book on your hand or on a table. So, there is a in the force or interaction between the table and the book, and there is a separate interaction, there is another set of interaction between the book and the earth. So, these two forces are really different. So, book B exerts a force, let us denote it at Ft on the table, then this Newton's third law, it says that this is the significance of Newton's third law, that it is easy to see that book B, because it is sitting on the table, it is going to exert a force on the table. So, the book is going to exert a force on the table, but the third law really says that the table must be also putting a force on the book, and that force is equal and opposite to Ft. So, this is the point of third law. Similarly, we can easily see that earth, the book has a weight, which means the earth is exerting a force W on the book. This is the weight of the book. Then Newton's third law points out that there must be a force, let us denote it by Fe, on the earth by the book, and this force is equal and opposite to the weight of the book. So, this is the gravitational interaction. So, these two forces are really different, the first one being is electromagnetic force and the second one being a gravitational force. Now, if you are not convinced that these two forces are really different, then perhaps I can, let us take a different example. So, imagine this is a ball, maybe a cricket ball, and so if the ball is sitting on your hand, then maybe you think that, well, it is not moving. So, there must be like there is a force of gravity and force of the hand and table, they are balancing each other. But imagine that you are this ball is moving, so and you are trying to catch this ball, so like catching in a cricket match, and then you can easily see that if the ball is falling with a great velocity and then it is going to hit the your hand, then the force exerted by this ball on the hand is really different from its weight. You will feel a force which is greater than the weight of this ball. So, this is a simple demonstration that the weight and the force between the book and the table are really different force. So, our point is that how to use Newton's third law of motion to solve problem. So, here I give you a step by step detailed kind of algorithm, if you may. So, how do we use Newton's third law to analyze mechanics problems? So, the first thing is that you determine which two bodies interact to produce the given force. So, suppose you identify the system. So, for example, let us say you are the system and earth is the surrounding. So, you and the earth are the two bodies that are interacting to produce a force. Once you do that, then the next point is describe the force on the system. So, if you remember that in the previous lecture we say that our picture for analyzing a problem is that we are dividing the universe into two parts. This is our system and this is the surrounding and this is the universe. So, describe the force on the system. So, this is the, if you are the system, then the force by the earth on you is the force. Now, the next 2 points are often not required to solve a problem, but you should complete the thinking, because it means that describe the third law counterpart as the other side of the interaction, which means that if earth you are the system and you are feeling the force by earth, the third law says that earth is also feeling a force by you. So, this is the what I mean by third law counterpart. And to appreciate the true meaning of the third law, So, you should remind yourself that how strong this counterpart force is and in what direction. For example, in this case you are pulling the earth upward by a force of magnitude equal to your weight. Let us now go to the Newton's second law of motion. Now, in this course we will emphasize on problem solving skill, developing your skill to solve not only the known problem, but also any unknown mechanics problem. So, this is going to be like one of the core concepts that we will be using again and again in this course. So, let us go through it slowly. Now, we want to cover all sorts of mechanics problem. So, what I am going to discuss is to give you 3 different versions of Newton's law. Is the same law written in a 3 different way, and each version is more general compared to the previous one. So, let us start with the first one. So, what does Newton's second law of motion says? It says that the effect of force. So, we all has an intuitive understanding from our experience what a force is. So, effect of force on a point particle is to produce acceleration. So, this is the statement of Newton's second law of motion. Now, note that acceleration is a vector which measures the change of velocity, the rate of change of velocity with time, and in turn it can be written as the second derivative of the change of position with respect to time. So, the point is that acceleration is something that you can directly experimentally measure from the information of the position and velocity of the particle as a function of time. So, to know acceleration or to define acceleration, you do not need to know anything about Newton's laws of motion. So, then what does this law says? It says that what is the cause of this acceleration, what causes this acceleration, and the answer is it is the force which causes the acceleration. In fact, the acceleration produced is directly proportional to the force applied on a point particle. So, force is the cause and acceleration is the effect. Now, if you replace this sign of proportionality by the equality sign, then the constant of proportionality is called is related to the mass. So, the acceleration, so this mass is a property of the object itself, it is not a property of the force that is acting on the particle, but the property of the object itself. So, acceleration also depend on a property of the object itself, and this property as we know is called inertia or the mass of the particle. Now, mass is a scalar quantity. So, you may recall our discussion from the previous week on what is a scalar and what is a vector. So, mass is an example of a scalar and its SI unit is kilogram. So, then we can rewrite this equation in a more familiar form, that the force is equal to the mass times the acceleration. Now, there are some situations in real life where the mass of the system that we are studying can vary, is not constant. Usually, typically in mechanics problems, we assume that the mass of the system remains constant, but this is not always the case. For example, if you take a packet of wheat to your nearest shop to grind it and get some atta or flour out of it. So, the shopkeeper will pour these wheat grains into some hopper, a machine which then runs and grinds it and makes fine powder out of it. So, in this case, if you notice that the amount of wheat that is going into the machine is changing. So, its mass is changing, with time. Another example which is shown on the slide is, suppose you have a weight machine, weight balance like the one you may see in large shops, and suppose you have a chain, and this chain was initially hanging fully from the air without any contact with the weight machine, and then you touch it, gradually lower the chain and touch the the balance, the floor of the balance, and then you release it. Then the part of the chain that is in contact with the floor of the weight machine is gradually changing with time. So, initially there was no part was touching, after some time all the chain will be falling on the weight machine, but during this time the mass of the chain that is in contact with the weight machine is going to vary. So, the weight machine, the balance will register a variable mass or variable weight. Another very common example is a rocket with various stages, like the one that is used to send people to moon or for Mars missions, etc. So, in this case, as when the rocket is lifted from the earth, it has a lot of fuel, and as it progresses more and higher and away, further and further away from the earth, then the fuel is consumed, and some of the part gets detached from the rocket, which gives a boost to the velocity of the remaining part of the rocket. So, these are examples of what is called variable mass problems. So, in this case, a slightly more general version of Newton's law should be used using the definition of momentum. So, as you know that momentum of a particle of mass m is the mass times velocity. So, p is equal to m times v. Then the Newton's second law says that the force which is the cause, it causes a change in momentum, and the force is in fact equal to the rate of change of momentum. So, F is equal to dp dt. Obviously, if you plug in the expression for the momentum, and if the mass is constant, then it reduces back to the familiar expression of force is equal to mass times acceleration, as we discussed in the last slide. Now, here I want to sort of make some remark on momentum. So, I sort of want to connect this course with some other courses such as quantum mechanics or electromagnetic theory that some of you may have are taking simultaneously in your curriculum. So, in Newtonian mechanics, such as the course that we are studying, so the momentum of a particle with mass m is defined as mass times velocity. Now, I must mention that here is a hidden assumption in this formula, is that the speed of the particle should be much smaller than the speed of light. If the speed of the particle is comparable to the speed of light, so c represents the speed of light. So, this is speed of light, then we need to modify this definition little bit, which is a subject of a course in special theory of relativity. However, so I want to make this point that in a course of quantum mechanics, for example, you have also come across another type of particle, which are, for example, the photons or the particles of light, and there you may have come across the de Broglie hypothesis that the particles of light also carries momentum, and this is given by a completely different formula. So, the momentum, so the photon, quantum particle of light is a massless particle. So, its momentum is given by this expression where k represents the wave vector or wave number, which is inversely proportional to its wavelength, times this universal constant called the Planck's constant. Some of you may also come across this fact about the massless particles carrying momentum in a slightly different version in a course in electricity and magnetism or optics. So, there you may have studied about electromagnetic radiation. So, this is very important, for example, in communications. So, like different kinds of radiation such as microwave and other light and X-ray etc. So, these are like very part and parcel of our modern life and technology. So, this electromagnetic radiation also carries momentum, which is related to its energy. So, the point I am trying to make is that the concept of momentum, as we see in these examples, applies beyond the scope of Newtonian mechanics. Now, you may wonder why momentum is so important. So, this is actually a sign that momentum is really something very useful concept. So, that people tries to apply the same concept in different and more different situations and try to generalize its definition. And where is this importance? The answer lies in the conservation of momentum. So, the law of conservation of momentum, we shall discuss it in the later part of this course. So, that is why people find the concept of momentum is so important. Now, coming back to our discussion on Newton's second law. So, we have covered situations where the mass of the system or particle is constant, and we have also covered in a situation where the mass of the system can vary, and still it does not cover everything. So, there is an important class of examples, for example, the collision problems, in which a large magnitude force can act for a very small duration. So, this on the left hand side is an example. So, this is a famous experiment or toy called Newton's cradle. So, this ball is hitting ball from the outside on the extreme end is hitting the ball in the one of the middle balls, and as a result one of the ball is moving out of the other side. So, this is an example of a collision. Now, in this case force may not be very well defined mathematically, that is the issue, because if you take the duration. So, the duration by which the force is acting during the collision is very small, the time window is very small, and the force. So, if you reduce the time window, the force becomes very large. So, this is a situation which is force is not mathematically very convenient to handle. So, we define another quantity called impulse, which is nothing but the force times the duration of the time interval. So, it is simply force times delta t. So, impulse is a vector, because force is a vector, it is multiplied by a scalar, the time interval. So, impulse must be a vector. So, note that I put it in a bold face to indicate that the left hand side is also a vector. So, its unit in SI system, its unit is Newton seconds. So, the unit of force multiplied by the unit of time. Now, I make a point highlight here that this definition can be applied to any force. That is, even though this is mostly when we think about impulse, it is very useful in situations where a large force is acting on a small duration. This is the typical situation of collision where this formula is used most often, but there is nothing in this formula that says that force has to be very large or delta t has to be very small. So, this formula impulse can be computed for any force. Now, using the concept of impulse, we can now rewrite the Newton's second law as the most general version of the Newton's second law, which covers all sorts of mechanics problem situations that I know of. So, how to write it? So, in the previous version we said that f is the rate of change of momentum. So, then if you multiply both sides by delta t, so we rewrite this formula as saying that a change of momentum, that net total change of momentum is equal to the force, the total force or the net force times the duration of the time window over which the force is acting. So, let me repeat, the change of momentum of a system, let us say a point particle, is equal to the net, that is the total impulse applied to the system. Now, this is probably not very familiar, this version of writing the Newton's second law may probably not very familiar to some of you, but we shall see that in some situations this is very handy to analyze the problems, especially in the collision problems and variable mass problems. So, now you know all three versions of writing the Newton's second law that covers all possible situations. So, now you know how to write Newton's second law. So, let me illustrate this third version in a graphically. So, it basically means that suppose the P1 was the momentum of a particle at the beginning of the interval and P2 is the final momentum at the end of an interval delta t. So, then this is P1. So, this arrow, this in the magnitude is P1 and direction represents the vector P1 and this arrow represents the vector P2. Then from the law of vector addition we know that this represents the total change of momentum of the particle during the interval delta t. Then the Newton's second law says that this total change is proportional to the total force. So, this F must be the total force the acting on the particle. So, note that the direction of this F and the direction of the change in momentum P2 minus P1 are parallel, that is they have the same direction, because that is the first message from this equation, that the direction, if you look at this equation, you must see that the direction of the delta P is in the direction of the total force. Now, this is an important point that which is so I illustrate it with this picture. Suppose this is our object, our system, and in most of the situations that we encounter in mechanics problems as well as real life, there are multiple forces acting on a single particle or a single system, such as there is a F1, F2, F3. So, there are three forces acting on this system. The momentum or the net change of momentum is given by not the impulse of individual force, but the total force. So, first we have to calculate the total force acting on the particle, which is the vector sum of all individual force, and then the net change of momentum will be in the direction of the total force. So, see that the net particle will move neither in the direction of F1, neither in the direction of F2 or in the direction of F3, but in a completely new direction which represents the direction of the total force. This is very important, and of course, the magnitude of the change in momentum and magnitude of the total force are not in general same, because you see that they are there is a factor of the time interval, they are not of the same dimension of course, and because of this time interval the magnitudes are also different, the numerical values are also different. So, we shall come back to this impulse in a later part, but Now, let us quickly illustrate the concept of impulse using a couple of examples. So, in this example there is a wall. So, this is a wall and there is a tennis ball which is travelling in the negative x direction. So, this is the positive x direction. So, this is the negative x direction. So, the tennis ball is travelling in this direction and it has a hits the wall and then bounces back. So, the question asks that the initial momentum is 2.8 kg per meter per second in along this direction. After the collision, the magnitude of the ball's momentum is nearly same. So, Pf and Py are equal in magnitude, but the ball is now travelling in the plus x direction, which means the direction is different. What is the impulse applied to the ball by the wall? So, before I go to the calculation, let me note two things. First is that momentum is a vector. So, this is a vector. So, even though the ball has same magnitude, the momentum before and after collision, but their direction is different. Hence, there is a change in momentum. So, delta p, which is Pf, the final value minus initial value, this is not 0. So, you have to consider the direction also when you calculate the change in momentum. Second point is that, so how do we calculate this change in momentum? So, note that in this case, this we do not know anything about the force that is acting between the ball and the wall. We also do not know that for how long the ball was in contact with the wall, that is the duration of the collision. But the beauty of Newton's second law is that even though we do not know this, but it says that because there must be a force between, because we observe that there is a change in momentum, which means that there must be a force acting on the ball, and the cause of this change in momentum is the force by the wall during the collision. So, we can compute the net effect without knowing either the force or the duration of the collision. So, how to calculate? So, let us first write. So, we have to be careful about the vector. So, we say that Pi is, so the magnitude is 2.8 kg meter per second, and it's, suppose we call this, we define an unit vector in the plus x direction as exact, then its direction is in the negative. So, I put a minus sign, and Pf, so these are given in the problem is plus 2.8 kg meter per second. So, then Pf minus Py, which is the required impulse. So, this is 2.8 minus 2.8 kg meter per second, which is equal to 5.6 kg meter per second in the positive x direction. So, the ball the direction of the force by the wall on the ball is in this direction. So, the next example. In this example, we will calculate the impulse due to gravity. So, a tennis ball, so this is a tennis ball of mass m is equal to 100 gram is freely falling due to gravity. What is the impulse due to gravity in a time interval of 1 second? So, assume that the acceleration due to gravity is 10 meter per second square. So, again in this case this is a situation in which we know the force acting on the ball, which is its weight m times g in the downward direction, and the time interval is 1 second. So, then using Newton's second law, so in this case we know the right hand side of the equation is given, left hand side is unknown. So, this is opposite to the previous problem. So, then we can calculate the impulse or the change in momentum the F times. So, in this case there is just one force acting on the particle. So, which is so the mass is, I am going to convert everything to the SI unit, so that I do not make mistakes with units. So, 100 gram is 0.1 kg times the acceleration due to gravity times 1 second. So, I am deliberately writing the units, so that you can see that they also play a role in the final calculation. So, what we get is 1 kg. So, this is meter second square in the denominator and the second in the numerator. So, one of them get cancelled. So, this is, and 0.1 times 10 is 1 into 1 is 1. So, kg meter per second. So, the units checks out. So, the point, the message here is that, again as I repeat, that impulse can be computed for any force, it is defined for any force, and there are typically two situations we encountered. One in which large force is acting for a short time interval. In this case, the hallmark of this scenario is that if you reduce the time interval towards 0, then the impulse remains finite. So, this is the situation where impulse is the natural way to analyze the problem. The other situation, like such as in this example, this force due to gravity is not large. So, in this case, in fact, this is constant. So, in this case, if delta t tending to 0, then impulse also tends to 0. So, this is a hallmark of a situation where the force is continuously changing. So, we shall, in the next lecture, we shall continue with the our review of Newton's laws of motion, and we will go into Newton's first law of motion. Thank you.